to the SEG Latin America Regional Advisory Committee's webinar series, Recent Advances and the Road Ahead. The SEG Latin America Regional Advisory Committee and myself, Laurie Background, will serve as your host for today's webinar. Before we begin, the model for this webinar will be a short presentation and an extended question and answer session. During the question and answer session, if you'd like to ask questions, please raise your hand in the webinar interface. Now, settings so that you can ask questions directly to the presenter. Alternatively, if you'd like to ask questions, you may enter them in the question and answer box. Today's presenter is Whitney Traynor Geotherm, graduate who graduated from Colorado School of Mines in 2001 with a bachelor's degree in physical engineering. 2002 to 2004, Whitney served in the Peace Corps, the Republic of Panama, advocating sustainable agricultural techniques, advising entrepreneurial endeavors by women's groups, and promoting HIV and AIDS awareness. In 2006, Whitney completed her master's degree in geophysics from Stanford University. She continued in Stanford's program of Earth Energy Environmental Science, of which she received her PhD in June of 2010. For her dissertation, she developed transferable value of information methodology for spatial Earth problems. She worked as a risk analyst at Risk Management Solutions and then a staff scientist at Lawrence Livermore National Laboratory for 4 years on quantifying the reliability of geophysical measurements for monitoring CO2 sequestration and geothermal exploration. In August of 2015, Whitney returned to the Colorado School of Mines Geophysics Department as an assistant professor, where she worked with machine learning and geostatistical techniques for integrating data. So without further ado, let's please welcome Whitney Traynor Geotherm.
Thank you, Laurie, for that really nice introduction. Yes, today I'll be describing my experience so far using distributed acoustic sensing, or DAS. And it mostly consists of 2 examples. The first being a geothermal application where we used 3D migration techniques to see what kind of subsurface structures we could recreate with the DAS data that we received. We also have a DAS grid in the middle of the Colorado School of Mines campus, and we were able to collect data for about 2 months. And we have some results to share with that, which is using more surface wave analysis or multi-channel analysis of surface waves. That's the MASW. And so we have these nice dispersion curves, and we were able to create some shear wave velocity models. So the webinar will consist mostly of describing these 2 projects. And before that, giving a little background on DAS in case those of you listening today have 0 background in it. So I'll go really quickly through this first slide because I wasn't sure how thoroughly Laurie was going to go over my background. But I'm originally from Idaho, Twin Falls, Idaho, which is on the south rim of this Snake River Canyon pictured here. So it inspired me to study geophysics at Colorado School of Mines as an undergrad. And then, as Laurie said, I headed to Panama for 2 years and then headed to a geostatistics research group in order to really learn about how to represent spatial uncertainty and to do uncertainty quantification, and specifically value of information methodologies for geophysics. And then 4 years at Lawrence Livermore National Laboratory gave me a lot of experience in geothermal and CO2 sequestration problems. And then I ended up back full circle at Mines in 2015, where my students have been looking at different stochastic techniques for understanding the uncertainty in our geophysical measurements. So to get started and to kind of give us some bearings about the DAS measurement, this is more a picture of what has been kind of the conventional seismic measurements that we've used, where we have a source on the left here, it's T-Rex, and this is a vibro-sized truck from the University of Texas at Austin that can provide both shear and P excitations. And this is what was used for our geothermal project that I'll be describing today. And then on the right, we have some people deploying the geophone, which has been the workhorse of geophysics the last many decades, and allowing us to make measurements of the displacement of the surface due to the waves that we excite into the subsurface. So we use a source, sometimes an active source like this fiber size, to hopefully see reflections from subsurface features that we're interested in. Here we're showing just, a very simple interface of different velocity values or density values. And from that, we hope to get reflected S waves or reflected P waves. And typically now we can use a 3-component geophone that will allow us to distinguish between movements in the X, Y, and Z plane. And so that will help us see when we're seeing a reflected P wave, which has inline particle and propagation direction. So the movement of those particles is in the same direction as the propagation of the wave itself. We can then distinguish that from S waves, where the particle direction is actually orthogonal to the propagation direction. And so that's, the power of this 3-component geophone. So distributed sensing, instead of using a geophone, uses fiber optics. And so here on the left, you see a spool of typical fiber that's used to help us have really fast internet. And it's been a decade or more now that this kind of sensing can be used for many different lines of business. So it can help us monitor how basically the status of a pipeline, can help us monitor the perimeter of an airport. It can help us monitor railways and the condition of the railways, if they're rattling or shaking too much in a certain area. And most importantly for this application, this webinar, it's been used in oil and gas to help us understand in the subsurface better. And so it started mostly because fiber was already downhole. And here's a picture of a casing for a hole that's actually being designed to actually fit the fiber better in order to get more measurements, or the measurements at different flow locations more. But they were already down there in order for our tools to be communicating with us up at the surface. And before I describe how distributed sensing works, I like to give this visual from ERTech. And this is showing the depth on the y-axis and time on the x-axis. And it was done during a fracking or stimulation job. So there was a monitoring well located away from the injection well. And what you can see here on the very bottom is the flow rate. So when they started stimulating. So when this flow rate becomes non-zero, that's when they started stimulating. And they're stimulating in this current stage, noted by this red arrow. And so we see when that flow rate becomes higher, what happens is there's now new fracture openings. And the fiber allows us to sense extension or compression. And so the extension is shown in red. And so we see extension when those fractures are popped open. And then in the layers above and below, we have compression because of kind of this opening in this current stage. And as that flow rate then drops back down to zero, you see a reversal of that trend. We now have extension in the intervals above and below, and compression as those new fractures close back down. So just a nice visual of what's going on, or what DAS can measure. So the DAS actually consists of kind of two main components. You have your interrogator unit, which is pictured here on the left, and that acts as the source of light and also the measuring unit. And then you have the fiber itself. And so there's two main attributes to the DAS measurement. First is the gauge length, which is like the width of the pulse, or how the averaging of is done over the fiber. And then the receiver spacing, which is the rate at which the light pulses are sent out from the interrogator unit. And so the gauge length ranges from typically from 1 meter to 10 meters, where the signal to noise will increase with a higher gauge length. And the receiver spacing can be as low as 10 centimeters, depending on if you have very specially engineered fiber. So what is in this fiber? If we look at a cross section, we have the cladding on the outside and then the core on the inside. And because of the many imperfections within this core, the light pulses that are sent out have many reflections back towards the interrogator unit. And so we can then sense all along that fiber because of all of those many reflections. And so that's what the interrogator's unit's next job to do, is to measure those light pulses that return. And so we can imagine at base conditions, when the fiber is not disturbed, those light pulses would return at a certain time. But if that fiber experiences some kind of wave field, that's going to either compress or extend that fiber. And those light pulses that return would return at a different time. And so we can measure that phase lag and relate that phase lag to the strain that is being experienced by the fiber. And that we hope that that same strain that the fiber is measuring can be related to the strain that's also being measured or experienced by the subsurface media. So compared to our point sensor, the geophone, there are many advantages to the DAS measurement, especially when we look at a vertical seismic profile. So that's what's pictured here on the right is the long well. So we can imagine that DAS could give us continuous receiver coverage instead of this limited geophone string. We can also deploy them in horizontal or slim boreholes. DAS can improve the repeatability of time-lapse because we can leave the fiber in the wellbore. However, there are fiber darkening considerations where the sensitivity of the fiber does degrade over time. If the fiber is already in the well, then that can be more cost-effective than deploying geophones. And we can also get distributed temperature sensing from that same fiber. And important to geothermal applications, the fiber can withstand higher temperatures than what geophones can because the geophones have electronics within them. However, there are some disadvantages. We have to consider coupling of the fiber. So how well is what is being measured in DAS, does it reflect what is actually being experienced in the subsurface? So if we look at the three potential ways that the fiber is placed in a vertical well, we see that we have different ways that provide either higher quality or lower costs. So if the fiber is cemented behind well casing, that will give us the highest quality, but will require a more pricey deployment of the fiber. Whereas on the far right here, we see a wireline deployment or a slick line. So the fiber is just loosely hanging in the borehole. This will likely give us the lowest data quality, but is the lowest cost. So the first part of this webinar, the data that I will be presenting was in a wireline deployment. And that again was because of the limited budget we had. However, I'll hope that I can convince you that we are still seeing signals that are reflective of what is in the subsurface. Additionally, DAS can be deployed horizontally and either can be done by trenching and burying this in the soil, or as is shown with many experiments at Stanford University, it can be using fiber that is just in a telecom conduit. And so it's just laying horizontally in that piping. For the second part of this webinar, I'll be describing some of the data from our main quad on Colorado School of Mines campus. And so if you look closely in that picture, you should hopefully see the fiber that is laying in that trench. So again, the first part of this webinar will describe some of the data and the imaging done from a vertical DAS that's deployed in a wireline scenario. And what's important to keep in mind is that we can think of this straight fiber optic cable as a single component probing device, where our component of sensitivity is along the fiber. So if there's particle motion along the fiber, then we will see that wave. So for body waves in our first example, we'll need certain incident angles where we can see either the P wave particle direction that's traveling up the fiber, or certain reflected S waves where the incident angle is more orthogonal to that vertical line, and we see the particle direction that is moving orthogonal to that. And so you'll see examples of both of those. And in the second example, instead of using a VSP and this fiber size truck, we'll be using ambient sources where we have recordings of a local earthquake and some ambient noise recordings. And again, our gas cable is horizontal in this case. And so instead of looking at body waves, we'll be looking at the horizontal component of a Rayleigh wave and also of the love wave, different surface wave. So really the outline of the remainder of the webinar is the first part, where we're going to see if this wireline vertical DAS can actually recover some fault structure. And in order to do that, we'll use reverse time migration in order to see if we can place in 3D where some reflections are coming from. So I'll describe that really briefly, and then I'll jump into the project itself and describe the acquisition geometry and show some of the data. And in order to kind of check ourselves on if we're actually seeing some of these signals, I'll be comparing the RTM images from the field data to some synthetic data using an a priori fault model. So our best knowledge of the area and what might be causing reflections. So whatever details that I leave out for this first project, know that you can access them on this open access paper that was published in February. So please feel free to follow up with me or to find that independently. The second part, again, we'll be using an earthquake and ambient noise instead of the fiber size. And I'll describe the Kafadar DAS acquisition geometry. Again, that DAS grid that's in the middle of our campus. And the postdoc that really worked on all this data came up with some really interesting theoretical developments that are due to the perpendicular fibers that we have on our Kafadar array. So I'll describe that briefly, and I'll show some of the shear wave velocity structure that was used using the surface waves recorded. His work has been submitted to geophysical research letters, so stay tuned. That hopefully will be published hopefully within the next few months. All right, so let's move on to reverse time migration. Again, this is our methodology, well, not our methodology, but the methodology you chose to place reflections in 3D space that were recorded on our DAS fiber. And so this method simulates both the source wave field, which is shown here in this animation, and the receiver wave field. So we need to have some estimate of the velocity of the media of where we're simulating, and the source wave field is mimicking the T-Rex or the vibra size that was utilized during our project. And so RTM propagates the source wave field forward in time, and then backward propagates the receiver wave field in time. And so this receiver wave field is either the recordings that we have from the DAS or synthetic data that will also be recording using that a priori fault model. And so our RTM then uses these two wave fields and defines what's known as an imaging condition, and does a cross correlation of these two wave fields in order to place, again, in space where potential reflectors are. And so here you see the shot index I and then the vector of spatial coordinates x and time t. And so by cross-correlating these wave fields, again, we hope to place in our image, which is this grayscale image here, where strong reflectors might be. So when we see white or black, that's where we assume there might be some higher reflectivity. So R is this kind of qualitative reflectivity. And so we will then hopefully reconstruct potential reflectors in 3D space. But as you see in this image here, there are some strong whites and blacks that are obviously not realistic geologic structures, and those are migration artifacts, which we also have to deal with in reverse time migration. And so when we don't have exhaustive coverage of either receivers or shots, we're going to have to deal with some of these migration artifacts. And as was showed in the wave equation, we have to make some kind of estimate of what the media's velocity is. And so when I referred to a PP image, that means that I've used the P wave velocity for both the source and receiver wave fields. If I referred to a P to S image, that's when I've now used the S wave velocity model for the receiver wave field. And that means that we're modeling or assuming that the reflections are S wave reflections. And so in some cases in this project, the S waves are recorded quite strongly. So let's talk a little bit about where the data was collected. This geothermal project was known as POROTOMO, and that's short for poroelastic tomography. And it collected basically a 4-week active seismic survey at Brady Natural Laboratory, which is close to Fernley, Nevada. This geothermal site has been operating and producing electricity since 1991. And so as you can imagine, there is a lot of a priori information from legacy seismic, different boreholes, et cetera. And so we used a regional fault model by Seiler and Falls to kind of extract where the local faults would be within our smaller POROTOMO area where these the active seismic took place. And so in this middle figure here, those green dots represent where T-REX or the vibra-size was active and basically injected energy into the earth. And you see here, these are 4 faults that we are curious to know if our DAS was able to see some reflections from. You'll also notice, we'll take a look at the map, that the well where the DAS was hanging was unfortunately in a very far kind of extreme bottom of the POROTOMO survey area. And so that, of course, is not ideal. Like we'd rather have the DAS in the middle of where all the source or T-REX locations were. So that is definitely a disadvantage to us when we make our reverse time migration images. I'll also note that there was about 130 meters of usable data in that vertical fiber. So we hope that we can make some reconstructions of these faults because faults serve as a really important recharge mechanism for the geothermal reservoir. Let's look at the data. So here on the right, I'm showing a zoom in of where the well is with the DAS fiber in it. And I'm looking at vibe shot 125, which is about 150 meter offset from the well. And so here we're seeing the channel index on the y-axis, which is pretty close to the depth from surface, and then time on the x-axis. So as annotated, we see the downgoing P and the upgoing shear wave. Now, if we compare this vibe shot to another vibe shot that is similar offset, 150 meters, but at 180 degrees azimuth from that one, again, we see the downgoing P and an upgoing shear. But the slope of that upgoing shear is much steeper, meaning it's much faster than that other location. So this is telling us right away that we have quite a bit of heterogeneity in this area. So just one other thing to keep in mind is that we have some really deeply dipping faults that are going to cause many different types of reflections that we might see. So here I'm showing an inline slice of one of the 3D RTM figures that we constructed from the data. And I want you to notice that the dark black are the actual faults projected onto that image. So it's from the a priori fault model. And then the grayscale, again, is the reflectivity from the RTM. And so we can imagine that at certain shots, we will have more sensitivity from a P to P, meaning a P reflection, off of a certain fault to our DAS well. So in this particular geometry, because of the incident angle, a P wave will be sensed by our vertical DAS. But in this other inline slice, we can imagine here, again, this black line is depicting that the far away fault that's dipping more southeast. And as that dip is changing here, we can imagine how if a S wave is reflected off at this angle, then the particle motions of that would be picked up by our vertical DAS well. So just again, to re-emphasize, DAS can be thought of as a kind of single component geophone when you're dealing with one straight fiber. And again, that I will be showing both P to P or PP images and PS, where the PS is using that shear wave velocity in order to propagate the receiver wave field. So the results, I'll zoom into 3 of these faults that we believe are there given previous modeling and previous data collection. And so I'll start by focusing in on what I call this middle western dipping fault, number 1. Then we'll look at the deepest western dipping fault, number 2. And then we'll look at that northeast dipping fault, which is the furthest away from our well. It's about 1 kilometer away from the DAS well. And for each one of these 3 faults, I'll be showing RTM images that are using 3 different receiver wave fields. A will be from a synthetic receiver wave field where we've forward propagated some data, assuming that this fault model was correct. And so in the case of A, there's no noise, and we've done the RTM on the correct velocity model that we know, basically, because it's synthetic. In B, we'll use the receiver wave field that is the actual data. And so these images will be noisier, and we'll also be probably using an imperfect velocity model for what is really in the subsurface. C, just again to really hopefully understand where some of those migration artifacts are in those images, we're going to give the RTM process a receiver wave field that is just random white noise. And so this will hopefully kind of check us on, okay, are we trying to interpret artifacts as structure? And we hope that C will, again, let us kind of see where those artifacts might be. So let's start with that middle fault, number 1, and we'll look at A, B, and C for that. So here's that middle west dipping fault, and we're looking at a cross-line slice. So we're looking at the more narrow cross-section of our porotomo box. And so we look at this synthetic image, and again, in these images, we want to look for bright whites or dark blacks. And what we see here is a really long white structure that seems to be very consistent with that, with the a priori fault. Again, these dark blacks are the projection of the fault model onto those cross sections. So now we can compare that to the same location and a PDS image, but using the actual DAS data as our receiver wave field. And what we see is, again, a pretty consistent structure that looks like what we got with the synthetics and is, somewhat in line with this a priori fault model. Now, just to check ourselves further, we do the RTM imaging with a receiver wave field of pure noise, and that bright structure disappears. So we can feel pretty confident that what we're seeing there in that image is from the fault and not just an artifact because of our non-exhaustive receivers and sources. So now let's move to the second, the deep fault. And now instead of looking at the cross line, we'll be looking at an inline slice and the cross line. And so here we're looking at the very top of that deepest fault. And in this time, we're looking at the P to P image. And so we see in the synthetics, a black structure that seems to be parallel with where we think that fault is. Now, if we compare that to the image created with the actual DAS data, we sort of see that structure is still there. Maybe not as strong, and there is more noise, again, because that's field data. In this red box, I highlighted that in this area, it appears to be some horizontal bedding that might be being reconstructed with the real data and RTM. We can also compare some of the consistency of the parallel structures here in this far right yellow box, comparing the synthetics to the real data. Now let's look at C, the receiver wave field of pure noise. And we kind of unfortunately see some of that structure that seems to be sort of parallel with that projection of the fault. So this tells us that maybe we're just seeing artifacts. And we won't feel as confident with this P to P image as we did with the P to S, looking at that middle fault. Now we'll move to that third fault, which is the furthest away from the DAS well. So remember, we're looking at this fault over here in the far kind of eastern corner, and here is the well again. And we're looking at this inline slice again, where this fault has a real change in its dip. And so here in the synthetic image, we see a really strong response in the P to S image of where that dip is changing. We see it both in the inline and the crossline slice. Now let's compare that to the real data. We see something pretty consistent. It's not as strong, but it's there right where that dip is changing. And it's in both slices. So now I can compare that to just pure noise. Well, we sort of start to see some of those migration artifacts here, but it's definitely, if we go back and forth, we're a bit, I'm confident that we're seeing some structure there. So just some takeaways from this vertical DAS project. We use this a priori fault model to sort of check what the DAS signal actually could pick up. And we saw in some of those P to S images, we were able to discern that middle dipping fault and some of the far eastern dipping faults that were about 1 kilometer away. And that middle fault, we actually could follow a long strike for about 300 meters if we look through all of those slices. The P to P image was a little more dubious when we compare it to the receiver wave field that was pure noise. So it's remarkable, but not unheard of, that this uncoupled cable is able to pick up signal. Because if you recall, this cable is a slick line or wire line deployment. It's just hanging in the well. And so we don't think it's unheard of because there's been publications on the Stanford array, which again is just laying in this telecom conduit, and it's able to pick up earthquake signals as well. And so these DAS fibers are quite sensitive. So now I'll move on to our horizontal example. Again, this was buried, our DAS cable was buried in the middle of our campus. So during some construction, one of my colleagues had the ingenious idea of using this as an opportunity to bury many geophysical anomalies in our quad. And at that time, I was able to convince them to also bury some DAS fiber. So in this kind of map you see on the left, the fiber was buried in essentially this grid that you see in blue. And the picture that you see on the right is this very bottom segment of the long axis. And so some of the anomalies that were buried in our quad are, as you can see on this map, were a UXO or unexploded ordnances grid, a dipping concrete slab, some dipping gas lines, and then this M is made up of various types of materials of piping. So we hope that this will inspire many future geophysicists throughout the years. You'll also notice here on the far right that there's an existing tunnel, and I'll come back to that in our data in just a bit. So the real summary of the results is that we were able to make about 2 months worth of measurement on our DAS cable. And from that, construct dispersion curves, so phase velocity versus frequency, and specifically able to do this for the separate Love and Rayleigh waves, and then use these to build many stochastic shear wave velocity models of the area under our Kafadar Commons that seem to be consistent with our best knowledge of the geology in this area. So again, our idea was to wrap the DAS fiber as shown in that map. And the fiber comes out here on the lower right and wraps up the short axis, about 27 meters, to this upper right corner. It then wraps the first long segment, or the long axis, and then comes down around and wraps the second long axis, the third, and the fourth. And after doing the 4 long axis or 90-meter segments, it then starts to wrap around the short axes like so. And the fiber actually continues as shown in the upper left map, but unfortunately, at some time during installation or some of the construction after installation, the fiber was damaged at about channel 600. So we only have 600 channels, or about 600 meters of fiber that's working. So we did have an interrogator measuring from about mid to late November of 2018 until late January of 2019. And luckily during that time, our array measured a small 3.6 earthquake from around Glenwood Springs. So that's about due west 180 kilometers from the mine's campus. And so here we're showing you the earthquake as measured by the DAS. And so A is a linear stack along the channels of the first 2 seismic signals from that earthquake. And then B is showing you for the 3 per channel along the time. So you can see that for each channel. So we have about 600 channels, as I said earlier. And these black lines are denoting the actual segments. So you see these larger 4 segments here are when the cable is wrapping around the long axis. D, C and D are just showing a zoom in at 56 to 60 seconds, where that second seismic signal is coming in from the earthquake. And so you can see here, the red and blue are denoting when the fiber is experiencing extension versus compression from those wave fields. And so Ben, a postdoc that was working on this data, very closely, did some, well, first made some observations here, which we worked on together, whereas if we look at co-located but perpendicular fibers, we notice an opposite polarity on some of these signals. So if we zoom in to channel 300 and 554, which is right here, and we reverse the sign of 554, then these signals seem to follow each other pretty closely. The same is at 282 and 509. Now I should back up and say that these wave fields here that BIN has superimposed over our DAS grid is to our best knowledge, the incident angle at which that Glenwood Springs earthquake hit our DAS fiber, and it is approximately 45 degrees for both cables, for both fibers. And so what this is saying is that at one point, at this 45-degree angle, one fiber is experiencing compression while the other one is experiencing extension. And so this is consistent with a horizontally transverse shear wave, which is what makes us pretty confident in saying that this is the love wave. And so what BIN did was some further theoretical development where he derived what would be the the strain field experienced by two fibers that are perpendicular from each other. And so that's what this expression is here, where E1 is the strain field experienced by, let's say, the long axis, and E2 is the strain field experienced by the short axis. And what you notice is that the Rayleigh components are of the same sign, whereas the love components, the second expression in each one of these, have opposite signs. And so when theta, which is describing the angle at which the fiber and the propagation direction are, is 45, that's when the love wave component is actually maximized. But when we have a theta of 90 or 0, then the love wave will deconstructively be combined. And so this is an exciting and useful result, and that allowed us to construct both separately a love dispersion curve and a Rayleigh dispersion curve using our Kafadar DAS array. So now I'll move on to the 3 steps of the multi-channel analysis of surface waves, or MASW. So again, we're using 2 ambient sources. The first one was the earthquake, which I showed some of the data of, but now I'm just showing some of the power spectral characteristics of the earthquake as compared to the background noise. So we see that most of the frequency is 10 hertz or less. And if we look at a spectrogram of that arrival of the seismic signals, we see even that most of the frequency lies below 8 hertz. And so now we can look at it for the ambient noise recordings as well, where we looked at different hours, chunks of hours at a time. And so here's a spatial distribution of the logarithmic energy of the DAS array, where this first image is from 1 to 2 a.m., so in the middle of the night on November 20th. And that first one is for low frequencies, 2 to 15 hertz, middle 15 to 25 hertz, and the last one, the highest frequencies of 25 to 40 hertz. And so what stands out is this high frequency range, how we have a lot of energy here on that farthest right short segment. And if you recall, I pointed out in the map that there's a tunnel right next to this segment. It's actually a steam tunnel that is delivering steam from the Coors factory to the campus. And so it makes sense that even in the middle of the night, there's some vibrations and energy going on, and our DAS array is picking up on it. Now we can make some visual comparisons of this to what does the energy look like in the middle of the day. So for the same day, but now at 1 p.m. to 2 p.m., we see that there is a bit higher energy in the two lower frequencies. So here's the middle of the night, here's during the day, and this should make sense because this is when students are walking across the quad to go to different classes. So the second step of MASW is then to construct dispersion curve from the data. And so a beamformer technique was used in order to fit the proper phase velocities with our data. And so again, because of Bin's analysis, he was able to both construct the Rayleigh wave dispersion curve and the Love wave dispersion curve, which is plotted here. And note that the dashed black line is showing the resolution boundary. So because our grid is only 90 meters in width, we don't use any of those dispersion curve values that are to the left of that boundary. On the right is the dispersion curve from the noise correlation functions. So there's one example here that's just a 5-minute recording chunk that's shown on the top. And notice that the frequencies go much higher for these types of ambient sources. And then on the bottom is for all the 5-minute chunks over a 4-hour recording. So we see that there's a pretty consistent pattern there in the dispersion curves. Lastly, we use a Monte Carlo multimodal inversion to go from these dispersion curves to a 1D layered model. And this allows us to get many different models that fit our data. And so on the left here, we see our best fit model for shear wave velocity in black. And then the shaded blue is showing our interquartile range for those values at those different depths. And we also plotted the Monte Carlo bounds that were given to the inversion. So some takeaways from the Kafadar Commons 2D perpendicular and horizontal array. We were able to use the multimodal Monte Carlo inversion from two different ambient sources to kind of complement the lower frequency from the earthquake and the higher frequency from the noise correlation functions. And Bin was able to see the Love wave from the earthquake, realizing that that the Love wave was going to be constructively suppressed, or excuse me, deconstructively suppressed during because of the orthogonality of these two fibers. And the fits that we had are consistent with our best knowledge of the geology in the area. So in summary, I think distributed sensing is a really exciting new sensor for us to use in geophysics, especially as an urban geophysical sensor. It's really tough to do many different types of geophysical applications in an urban setting because of noise. But you can imagine with this kind of sensor, noise can be the source, and DAS seems to show a lot of sensitivity, even though it might be in a conduit, etc. DAS and all distributed sensing provides really high dense spatial and temporal sampling and allows for extreme temperature environments as well. I think there's a huge need for developing new techniques to be able to probe some of this data for signals and for useful information. Again, we were only recording for about 2 months and we have 20 terabytes of data. So imagine, not being limited by your interrogator. It will be quite daunting to know which data is most useful. And coupling, of course, is a huge challenge ahead. I think we've showed in the first example that even though it's not an ideal deployment of the vertical fiber, we're still able to get signals that are consistent with the geology. But to have better understanding of that and to account for it, we can only improve our results. So I'd like to acknowledge, of course, Ben, the postdoc that was working with the Kafadar data, and Ebru, my colleague at Colorado School of Mines, who helped a lot with the surface wave analysis. And then this, the Kafadar was possible because OptiSense provided 2 months of the interrogator in order to make these measurements. And my former department head, John Bradford, really helped make sure that we could get a place for the interrogator and funded Ben's work as well. So with that, I'll stop and I guess open it up to questions.
Thank you, Whitney. Wonderful presentation. I thought it was very informative, at least for myself. I didn't know too much about DOTS and how it could be used and some of the challenges. So it was really interesting to me. We do have a question, actually a couple questions here. One is from Ana Corcio from Argentina, and she was wondering about the impact of ground roll in the DAS VSP application. And also like to ask about the energy loss in DAS in general.
Okay, so ground roll for the first application, we were only looking at 150 meters below the surface. So from my recollection, we didn't see any ground roll, but I know that that definitely it can be a problem for active seismic. As far as for the earthquake data, I mean, I can only go back to the data that I was showed, and I'm not sure, you know, it would, we interpreted these as surface waves, and so I assume ground roll is a surface wave as well, but I couldn't tell you if we distinguished a ground roll from what is shown here or not, if that answers the question. And then I think the last part of it was about, do you mind repeating, Laurie, something about energy?
Yes, Anna wanted to know if you could tell her a little bit about the energy loss in DAS in general.
So off the top of my head, I definitely couldn't give you a formula, but I know that there is measurements of up to 20 kilometer or more fiber. But again, I don't think I can't give you an actual equation of what that loss is. And I just know that it might somewhat be related to fiber darkening. So over time, the fiber will definitely lose its reflectivity. And so you'll lose some of that sensitivity over time. But again, I can't give you a good equation off the top of my head, unfortunately.
Okay, thank you, Whitney. I'm kind of curious what you see the next step in DAS, what that might look like. Where there might be people really pushing the envelope.
So I think one thing to keep your eye on is definitely, well, there's an SCG is being involved in the smart cities. There's some kind of smart cities conference going on. And so I think, again, just methodologies to probe the mass amounts of data that could potentially come from, very long fibers over over long periods of time. That's, what people are going to be looking at. And so, this smart cities, how can we use these kind of sensing to know, is there a water leak before some kind of damage occurs, or a sinkhole? Mm-hmm. And as you see, this image is courtesy of my colleague Eileen Martin at Virginia Tech. They have used DTS for a lot of glacier kind of understanding, and I believe they're starting to use DAS as well. But to me, I think the main, really where I'm excited is seeing it as an urban geophysical tool. But it's going to take a lot of new development to really be able to deal with the large volumes of data. Right.
And about these large volumes of data, you measured for 2 months and you had 20 terabytes of data. That's a very, very large amount.
Yep.
Are there currently efforts as far as employing machine learning or AI to start to chew on this data and be able to quickly get to some sort of yes or no?
Yes, and I should also say that I believe at Stanford, you know, they've been collecting for years now, and so they do a lot of kind of downsampling of the data in order to deal with that. And also, I'm not going to remember her last name, but she's also at Stanford, and she's working on machine learning techniques in order to do exactly that, to kind of mine where the interesting signals are, because you are dealing with so much of it. So yes, I would say work at Stanford. Eileen is looking at ways to be more efficient about ambient noise recording. So how many of those noise correlation functions do you actually need in order to build models and see if there's changes going on in the subsurface?
Thank you. We have a question. Was there any surprising in your experience in this DAS setup? Was there anything out of the usual that you weren't actually anticipating? Because it seems that things were pretty straightforward in these cases.
Well, so for the first one, they had initially planned on packing the well with sand. So they had put the fiber down the well, and then they were going to pour sand around it in hopes of improving the coupling of the fiber to the actual media. But the fiber broke when they did that. So the sand, actually, the weighing of the sand broke the fiber. So they tried to be more creative than just having it hang there. So that was one unexpected thing. And I would say that, to me, these results were unexpected as well. Like, I know not all of them are absolutely convincing, but this one to me is pretty convincing, that we're actually seeing structure that's due to that fault, and it's from a fiber like just hanging in the well. So and again, we tried to be realistic and to check ourselves by comparing it to just pure noise. So I would say the results were definitely surprising to me. And yeah, our Kafadar Commons, when we set up the grid to be orthogonal like this, it was really just trying to maximize our sensitivity to different directions. And so it's pretty neat that it ended up being that because of this perpendicularity, we could actually exactly see the love wave or find the love wave. But we are also super lucky that it was because of the angle of incidence of that earthquake.
Okay, thank you. Any other questions? Well, I don't see any additional questions, Whitney.
Okay.
So with that, I'm going to say thank you, Whitney, and all of you for attending the SEG Latin America Regional Advisory Committee's webinar. As part of our webinar series, Recent Advances in the Road Ahead, please look forward to our social media posts to register for future interesting talks. And thank you again for attending today. And thank you, Whitney, for a very interesting presentation. And until next time, have a great day. Thank you.
Thank you.